With AWS, and with me on stage I have...
I'm Esteban Kuber, principal engineer in the Rust platform team at AWS, and I'm also a member of the Rust compiler team.
Before we really get started with this presentation, I did want to get an understanding of the audience, who we have here. We're covering a lot of different topics through the next hour, and so we wanted to get a feel for what areas we should emphasize, where we might want to deep dive, and where we might want to just hit the high level. So to start out with, raise hands if you have, your primary activity is software development. Okay, most people. Okay, good. All right, in software development, Java folks? Okay, Rust? Okay, handfuls of both. Everybody familiar with Lambda? Okay, and Graviton? Okay. Any SREs? A few. Okay, great, thank you very much. That'll help us kind of customize this talk as we move forward. So, great, so let's talk about sustainability in the cloud with Rust and Graviton. When we talk about Rust, as some folks know, Rust is a general purpose multi-paradigm programming language. It's a compiled language. You download a compiler, you compile your source code, and it ends up as machine code. Esteban's going to go into a lot more detail on some of the features and what we see specifically between Rust and Java. And then Graviton, we have Graviton 2 and Graviton 3 instances. There's some original Graviton as well. But Graviton is a custom silicon ARM-based processor made from Annapurna Labs, which is part of Amazon. So when we talk about Rust, there's kind of the official aspects of Rust, and then how the platform team actually thinks about the language and the compiler as they're thinking about evolving the language. And Esteban's going to go into that a little bit.
Yeah, thank you. To be clear, this is not an official motto, but it's the way that I usually explain to people, particularly developers, the general approach that in the Rust project and the Rust community we take for correctness, safety, and performance. We acknowledge that there are problems that are unsolvable if you try to tackle the entirety of it. But if you limit the scope of the problem, if you focus on the 80% of it, then you can statically check it, and it's much easier, and you gain a lot of performance, safety, without having to address the harder problem. And you can see it in Rust from the way that it manages memory, and but also throughout all of the projects, not just the language, the tooling, and the larger ecosystem.
Great. And Esteban mentioned performance and reliability. Those are two of the three official Rust pillars that we try to look at when we look at evolving Rust. You know, how do we maintain the best performance with the greatest reliability and the greatest productivity? So starting with performance, when we have performant code, we're going to have code that's using fewer resources just because it's literally executing on the CPU less. It's using less instructions, allowing the CPU to use less energy, and fewer resources overall. From a reliability standpoint, we get into fewer retries, right? We have code that's reliable, it's going to fall over less. We can count on that code to always be running. That's going to allow our systems overall, again, to be using fewer resources. They're going to have to recover from failure less often than they otherwise would. Also, in terms of reliability, Rust has reliability built in from the start in terms of memory safety, which is kind of the thing that Rust is famous for. But in terms of creating a language that was built around this core principle of reliability, memory safety was a huge thing, but also correctness. So you get linter features actually built into the compiler. You've got ancillary tools that come along with the Rust ecosystem, things like Clippy that will provide additional linting. Cargo has some safety checks built into it as well. For instance, you can't delete packages once they've been published, which has been known to be an issue with some other ecosystems. So this idea of reliability is really baked into the language in many ways, and not just from a memory safety perspective. Lastly, from a productivity perspective, Rust is built with the idea that we don't want to be sitting in an ivory tower designing something that nobody can use. Well, we want to be practical about how developers can approach the language and use the language. And so it's important from a Rust perspective to be able to have developers code in the language with less testing and be more productive. And that, at the end of the day, is also going to use less resources in build and test. And then when we get into production, we'll be doing so a lot faster. All right. Graviton I'm going to touch on, and then we're going to switch back to Rust for a while, and we'll loop back around to Graviton. But the AWS Graviton processor, the Graviton 3 processor is the latest generation. We just had a new instance type actually announced last night, also built on the Graviton 3 processor. But the Graviton 3 based instances use 60% less energy for the same performance. And we're going to show some charts and graphs later on in the presentation. You're going to see some interesting numbers in here, things where, sometimes we talk about Graviton being a whole lot faster. Well, it depends on the application. And so in some applications, you're going to see huge performance increases by using Graviton. But the key stat for this particular session is the sustainability axis. So we want to concern ourselves with how much energy is actually being used. And consistently, we see Graviton 3 based processors take 60% less energy. And you'll see those reflected on the graphs that we show later on. Graviton 3 uses 3 sockets per rack. This is something that James Hamilton had talked about when this processor was first announced. But that's a huge boost to the sustainability story for this processor. Again, we'll talk about a little bit of this later on. So when we talk about Rust in comparison with other programming languages, Esteban and I sat down and we put together this chart. This isn't a hugely scientific chart. There are some numbers behind this, but we didn't want to get too specific because benchmarks get a little wonky and hard to justify sometimes. But as a general rule of thumb, this is what we're looking at in terms of sustainability with various programming languages. There's a lot of data on this slide, even without the numbers. But I think the way to observe this chart is that there's 3 major categories of languages that you can see on the chart. C#, Go, and Java are all languages that compile to kind of an intermediate state, and then they need additional runtime help. So we have kind of a 2-part. Part of it's done at compile time, part of it's done at runtime, either through platform runtimes or intermediate code that's being JITted. These types of activities are going to use up more resources at runtime. So looking at some workloads, you can see you don't get the best sustainability story from those languages, although it's not bad. The next 3 that we look at here, Node, Python, and Ruby, are all interpreted languages. So at the end of the day, we need to get text in the form of source code to machine code. And in these 3 instances, we're doing all of that conversion directly at runtime. You install the interpreter on your production platform, and then you run the code. And we're going to see worse performance from a sustainability standpoint than other languages because of that. And then finally, on the Rust side, this is compiled. Everything's done ahead of time, and at the end, you have machine code that you copy out to your production server and run it. And we see the best characteristics from a sustainability perspective from Rust. So we wanted to take a look and get more than just this graph, but doing so with this many languages. These were picked because they're popular and they're used quite a bit. But we wanted to take Java specifically for 2 reasons and really do a deep dive on comparison between Rust and Java. Java is a very popular programming language. It's used a fair amount, and it has the convenience of being within Amazon. The Java team collaborates very closely with the Rust platform team. So Esteban worked with the platform team to do a deep dive into that. And I'll let him kind of explain a little bit more about the comparison between the 2 languages and then what we found doing some light benchmarking.
Thank you, Emil. And before I go over this slide, there is another axis in which Rust and Java have a huge commonality. Java was started in the 90s with the objective of bringing memory safety and performance to embedded devices and networking appliances. Rust was envisioned in the mid-2000s as a way of getting high performance with memory safety. The unofficial, one way of talking about what the objectives of these 2 languages were is bringing the performance of C++ without the segfaults and CVEs. And C++ is a great storied language, but this is a reasonable thing to try to tackle. The interesting part is the 2 languages, Rust and Java, took very different approaches to tackle memory safety. In some cases, diametrically opposed. Rust doesn't have a runtime. Well, it does have one, but it's a very small shame on top of your platform. It's in the same sense that C has a runtime. Java, on the other hand, has the virtual machine, an incredible piece of engineering, but it has a cost, an associated cost, both when you're starting your application and during the lifetime of your application. Java uses a dynamic dispatch by default. It uses vtables. This is a fancy way of saying every time you call a method that has generics, at runtime, the application has to figure out what type is actually interacting with. And that implies chasing pointers in order to find the correct method. That is pretty bad for cache locality, which in turn affects general performance. Rust, on the other hand, is monomorphic by default. And monomorphization is a very fancy way of saying the compiler looks at every invocation of your methods that have generics, sees which types it actually was called with, and it generates code for each one of those. That means that when you call a generic method on Rust, by default, it's going to be just as efficient as calling a function that didn't have generics. On the Rust side, you have stack allocation by default. It means that when you're writing your code and you declare a new binding for a given type, that is going to end up in the stack. In order to store something on the heap, you have to opt into it. You have to use the box type, which is just it's just a type that is used to tell the compiler that what you're dealing with is a own pointer into the heap. Whereas in Java, the only things that are stack allocated, at least for now, are primitive types. Everything else, every object, every class that you have defined and ends up instantiated into an object has some overhead, and it ends up in a JVM managed heap. The JVM heap allocator is incredibly fast, but you are going to be allocating a lot of objects. One big advantage that Java does have on Rust is that it has a just-in-time compiler. The JVM, as it's running, is looking at the way that your application service is actually running and can optimize the code that is actually being executed to the workload that is observing. Whereas Rust is ahead of time compiled. Once you have compiled it, the binary is not going to change. That can be an issue, depending on what on the optimizations the compiler does ahead of time, and can be an issue depending on your workload. There are other general differences. For example, because Java has runtime, it can afford to have reflection, whereas Rust doesn't have that, but it has hygienic macros, which means that you can apply some of the patterns from Java in Rust, but everything happens at compile time, but it has limitations. But there are other differences. Rust has async await as part of the language, just like C# and Python and other languages, with some slight technical differences, whereas Java doesn't have that at the moment. And it has maybe one of the biggest, after memory safety, one of the biggest things that Rust is known for, which is the dichotomy of safe and unsafe Rust. Safe Rust ensures at compile time that memory safety invariants are maintained. Unsafe Rust has been described by some as it turns off the borrow checker. That's not what it does. Unsafe Rust is just safe Rust that allows you to interact with pointers. You can dereference pointers, you can call C, ABI, FFI functions, including syscalls, but that's all it does. All of the other assurances of safe Rust still exist in unsafe Rust. When it comes to the specifics about how these two languages deal with memory, they have huge implications on the performance. I've gone over some of these already, the stack allocation by default, having to opt into heap allocations. And in Rust, you have to actually think about these things when you're designing your application. In Java, because you are relying on the garbage collector, you have much more freedom on what you can express, which can be both a blessing and a curse. Rust has some limitations on things like trait objects that can be represented. Java has the just-in-time compiler that can make your application just as performant as a Rust application, and we're going to see that. But the main difference is Rust is focusing on zero-cost abstractions, and that is a concept that we are borrowing from the C++ community. By the way, zero-cost abstractions doesn't mean that your abstraction doesn't have any cost. What it means is that whatever abstraction you're using, once it gets compiled down to the final binary, it's going to be just as efficient as the assembly that you would have written while all the features that you were leveraging are being used. Those differences in approaches come with trade-offs, like everything in tech, like everything in life, really. And all of the specifics that I've just mentioned do not come for free. For example, Rust by default uses the system heap allocator. And that is significantly slower than the heap allocator in the JVM. And you can bring your own allocator. You can, for example, use GA-malloc, and I've seen some use cases where there was a 20% improvement just by swapping the allocator. But you have to think about it. you have a type system that ensures memory safety at compile time without garbage collection. But the kind of patterns and the kind of data structures that you can express with that system is limited. It forces you to have very clear ownership rules. Representing a tree is fairly trivial. If one very common example that people like to mention is linked lists. A single linked list represented in Rust is fairly trivial. You have an ownership to the first node, which implies ownership to the full list, and every element after that is owned by the previous one. Trivial. Rust doesn't have a problem with that. But as soon as you have a doubly linked list, where every node has to have a pointer to the next element and to the previous one, safe Rust cannot represent that, which is a problem. If you are trying to represent things that look like graphs, Rust is going to get in the way of you, particularly if you are not trying to change anything else about your algorithm. Having said that, there are ways to sidestep this, effectively do what the JVM or any other runtime is doing for you. You can have, for example, an arena where every node is pointing and the index into that arena for a doubly linked list. That actually has performance benefits because now every single node is in a single section of memory and cache locality is much better. You can also use unsafe. You use unsafe, you are back at what you would have written in C or C++. But this is friction. You end up having to unlearn patterns that used to work in other languages and learn new ones that are more amenable to the kind of code that Rust is happy with. Because another trade-off is you don't have runtime reflection. You can express it within the language, but you end up having to implement all of the code that you would have for that. You could have a plugin system, but if you want to provide access to your internal data structures to the plugin to introspect what your application is doing, you're going to be writing a lot of that code yourself. You're going to have to provide those APIs. And related to that, Rust doesn't have a stable ABI. There is a way of having a stable ABI with Rust, which is through the C ABI. But again, you have to think about it. You have to opt into it. You have to write code at the edge as if it were C and not Rust. All of this contributes to this feeling of having to fight the compiler when you're trying to do these kind of things. All of this is why Rust can be considered a difficult language. In the JVM side, on the other hand, you have very different trade-offs. It tries to make things as easy as possible, and it optimizes for the kind of patterns that Java applications see. Allocating objects is very fast, but you're doing it a lot. Memory management is much easier because it gets out of the way. It lets you express any data structure that you wanted. But because there is no pushback, if your team or yourself are not sufficiently restrained, you can end up with a very difficult layout in memory that is difficult both for humans to understand and for the machine to execute efficiently. Of course, on the Java land, you do have native compilation as well. You can leverage Graal, and we're going to show the kinds of wins that you can have with Graal. But you still have penalties for startup times. Particularly for short-lived processes, all of the costs associated to the JVM get amplified. So as Emil mentioned earlier, the Java team at AWS and the Rust platform team at AWS, we are somewhat sister teams. We are under the same umbrella. And we do have a lot of back and forth on trying to understand each other, understand the problems that we're facing, and understand the solutions that we have applied to similar problems. And as we were having these kind of conversations, we came up with the idea of, okay, let's try to make an apples-to-apples comparison. Let's write an experiment. Let's get two developers, a Java developer and Rust developer, writing idiomatic code, doing exactly the same thing. And try to see not only the performance differences, but also try to get an idea of how the experience of developing these applications was. Try to get an idea for what the rationale for the decisions that were made were. And of course, we did that. We decided to use a Python-based application as the baseline called Magic Wormhole, which is a very simple networked application that lets you send files from one machine to another. It's the simplest possible networked application that you could come up with. You have a receiver, which is a process running where the file is going to be stored to disk. You have a sender, which is reading from disk and sending bytes through the network. And we have a registry, which is a poor version of a DNS registry. Is a way of having the receiver say, this machine at this IP address is under the name of foo. And then from the sender, I can say, I want to send a file to foo. And it's going to figure out, OK, this is the IP address and TCP connection that I need to connect to. Once that is done, the registry is no longer in play for file transfers. And as I described, it's very simple. But one of the things that we tried to do is we wanted something small, something that could be accomplished in just a couple of days, if not faster. Of course, as we're going to see, we ended up going through multiple iterations because of multiple reasons, including human nature. But we also wanted it to be relatively small so that you could read it in a single sitting and fully understand what was going on in the application. For the Rust version, I decided to use async await. This is a networked application. It made sense to do that. And this is, of course, not the full application. This is just a snippet, and the last two lines are inside of a loop. But effectively, all that the application is actually doing is allocating a fixed size buffer, reading from a TCP connection into that buffer, and writing from that buffer to disk. Nothing else. Because we ended up with multiple iterations, we used different libraries, but if you are familiar with either Rust or Java, all of these libraries will be familiar to you. We also wanted to have an extra data point, so we didn't just run the Java version on the JVM. We also compiled it using GraalVM. And the first iteration of Java, we used an HTTP service, an HTTP library to actually send the files through. And that meant that the Java version was actually quite a bit slower than the initial Rust application. And the Rust version, I also made a few small changes to try to use a blocking version and see what the overhead of async await could be for this case in particular. And of course, the second chart is the GraalVM version. So you can see that the JVM version is quite slow. The GraalVM version has a huge improvement in this case. And the two Rust versions are the fastest in this case, with a bit of difference, but not materially so. But of course, human nature is, particularly as technologists, as soon as you are faced with a mirror showing you, oh, you're actually being slow, the first reaction is, oh, okay, I need to improve. Let's see how I can get things better. So to our colleague's credit, he went back and completely rewrote the Java version to actually use a TCP connection. And the results were much starker now. Not only the Java version and the JVM version and the Graal version are fairly similar, now they are faster than the original Rust version, which of course made me go, okay, I need to figure out what the problem is on my side. The tall chart is the original async version that I had written, which is half as slow. The last bar, the 2 bars that you see there are actually the time after I completely removed the calls to the Tokyo runtime. And this was a surprise to me, and including some of my colleagues. We found in the Tokyo library, just by being around in this application, was severely impacting the file system I/O performance. And this is something that we still have to dig deeper into figuring out how it can be mitigated. But it's, I think, a great point to take away. You need to measure. Until you measure, you don't really know what you're actually going to see. So after I took Tokyo out, we got roughly the same performance. And we did, I did a further iteration where, okay, I was using async await, which let me send multiple files using a thread pool. I took that out. Okay, what can I do? I took the blocking version, and I added a thread pool. And you can see that having the thread pool around with 1 thread per core, there is no penalty to actually having that. So now I can send as many files in parallel as I wanted. And we ended up all roughly with the same performance. I did a further iteration that is not represented here. I went down to actually performing a send file syscall operation to see how much faster I could get, and it was exactly the same as this. So we are at the limits. At this point, we are effectively benchmarking the I/O operations, both on the network and on the file system. But even though the throughput was matched on both versions, the story is a bit much more stark on the resources that were utilized. This is the first iteration of the Java version. Of course, as we said, that is an apples to oranges comparison because it's not really the same. They are not doing effectively the same, but it was quite a stark contrast. On the second iteration, that was actually faster than the Rust version, we still have issues with the memory consumption. One thing that I want to highlight is how significant the improvement of using Graal VM for this use case was. And of course, Graal VM has some limitations. If your libraries are using reflection, for example, you cannot use it. But if you can, and you haven't measured it yet, that would be an incredibly easy win to do today. The final version, Rust memory consumption remained roughly the same. The Java memory consumption was orders of magnitude higher. And it makes sense. In Rust, I'm stack allocating everything except the buffer. The buffer is size bound. And I only have 1 buffer per concurrent file. So the memory usage of the Rust application is very predictable. And it doesn't need any overhead. Like, for example, in the JVM, every object has a per object penalty to be able to know at runtime what the superclass, what the class of that object is, what the superclasses of that class are. All of that adds up. By the end, we had multiple iterations of both of the apps in both languages. We had to drop the Tokyo runtime to get a significant performance improvement. We added support to use syscalls directly and didn't really materially impact the performance. And we added support for a multi-threaded file sending, which was literally 2 lines of code, including modifying the cargo lock, the dependency management. Whereas on the Java version, on the Java side, we had 4 iterations. We used the initial version, which was relatively slower. We used the standard library I/O. We used native I/O. And in order to remove some of the variation that we were seeing in the benchmark, we replaced where we were writing the file to disk. Instead of writing to an SSD, we ended up writing to a temp FS in order to remove that penalty, which was actually impacting quite a bit Java more than Rust, but it was impacting both. And there are some interesting takeaways. Writing the applications was actually quite easy for both languages. There were some issues both in Java and in Rust, but getting this up and running took only 2 days. The iterative process of benchmarking and optimizing took longer. But it can also, depending on your workload, it may be that you are not looking for optimum performance, you're looking for good enough. If you have 2 options and one is faster than the other, you can just go with the faster option. If you don't need more than that performance, then it's fine. In real life, you may be throttled by your use of a database or even by Memcache. It depends entirely on what your workload is and how your application is written. For things like command line utilities, in my mind, it's a no-brainer. You really don't want to use short-lived applications in the JVM. All of the penalties are exacerbated, and none of the benefits actually kick in. One thing that we anticipated, but it's still worth calling out, just writing to disk. You have to consider the latency of flashing to disk. You have to be very careful not to flash tightly in a loop. Those kind of things can materially impact the performance when you are micro-optimizing. We also were pleasantly surprised at the performance, how the Java performance ended up being. We ended up having relatively the same performance. In some cases, it even was better than the Rust version. But of course, as we anticipated, the Rust version resource utilization was much better. And of course, as I do have to mention, the libraries ecosystem in Rust, because it's a newer language, is much greener. There isn't as much a breadth and long tail of libraries available as there is in Java, although some of that long tail in Java is actually not as up-to-date in the patterns that they follow.
We've been talking a lot about Rust, obviously. So what's the Graviton part of this conversation? So after that experiment had been completed, we wanted to see what it looks like to have a combination of Rust versus Java and x86 versus ARM using Graviton in the cloud. What do we see from a performance perspective? And what do we see from an energy efficiency perspective? And how does it impact cost? That cost isn't all as important for what our primary concern, because we're looking at sustainability, but we still wanted to have an understanding of what that looked like. So we turned our sights to a few sample applications. This is a really handy sample application. It's been re-implemented in multiple different languages. It's available open source on GitHub in the AWS samples area. Each one of the languages will point to all the languages it's been implemented in. Just for consistency, we stayed with Rust and Java to be able to capture metrics and then be able to see what things look like in a point of time. One thing to keep in mind is that each one of these ecosystems is evolving. Things change all the time. We just had Lambda Snap Start released, and that's going to change at least the cold start performance aspects if you're using Java Corretto 11. So, as time moves on, everything's going to change, but we wanted to get a sense for what it looks like right now. One change we did make, most of the samples are using 128 meg Lambda functions, but the Java sample was using 256. So we changed it to 128 just to be consistent. Things work just fine. Numbers changed a little bit. In Lambda, when you change the memory that's allocated to the function, the CPU will also change accordingly. So we wanted things to be the same as much as we could. And then we had to make minor changes to both applications to be able to capture x86 statistics as well as ARM statistics on Graviton. So we ran the numbers and compiled them, and then from a performance perspective, we saw these numbers between Rust and Java. Do you want to talk a little bit?
Of course. Thank you. So there is each one. What you can see in the chart is multiple endpoints of the sample applications. They are performing different operations. They have different costs associated to them. They are all interacting with a database in both cases. And you can see the aggregation by Graviton 2 and x86. One thing that is fairly consistent, the yellow line is the P50 latencies. Of course, they are the lowest. You can see the increase as you go to P90 in orange and P99 in red. And by the time you're measuring the P99 latencies, what you effectively end up doing is measuring the latency of talking to the database. That is going to be really what you're seeing. But it is still informative to see what the constant factor latency that each language brings. I do have to clarify, these are latencies for warm starts. So it means you're hitting an endpoint for a Lambda function that is already running. It's not the first request. And I also have to point out the x-axis of these two charts is not the same. You can see that the Rust latency is actually quite a bit better than for Java.
You also notice that when you look at the charts, there's four major buckets. There's four major operations in the sample application. It's effectively a create, read, update, delete, a CRUD application. And so there are multiple operations here, something that gets all the products, something that gets a single product, something that gets that deletes a product, and what's the one that puts in a product into a database. So this is a Lambda with a DynamoDB behind it, and then we break down each one of those operations into Graviton versus x86, so you can see. And on this graph, you'll see, sometimes performance is about equal. Sometimes you'll see one's a little bit better than the other. Go ahead.
Yeah, and part of the reason that we are showing maybe this chart that can be a little bit more crowded than we otherwise would is precisely to show the different use cases within the same application, because it's not necessarily obvious that those operations would have the same cost in the two languages. But this is just latency. We also wanted to look at the energy usage of the two languages, and we removed the x-axis, yes, I know, because it was more interesting to us to see what the relative cost was within the same language. And this goes to show more about what the energy costs within Lambda actually are for the application.
And we see across the board, Graviton outperforming x86. So if you focus just on one language or the other, it doesn't really matter. You'll see each one of the operations, Graviton outperforming x86 from an energy perspective.
And it's not just energy usage, of course, it's cost as well. And if you look at, again, these two charts don't have the same x-axis, but you can see that both for x86 performing exactly the same operation with exactly the same throughput, latency, sorry, the cost between Graviton and x86 is lower, which is reflecting the lower energy consumption. And if you look what the difference is between Java and Rust, you can see that you can perform exactly the same amount of work for cheaper if you are using Rust. And in this case, you are, as I mentioned earlier, we are limited by the latencies introduced by your database operations. If you have a more CPU-intensive or memory-intensive workload, then you can further leverage the benefits of Rust to lower the cost of running your application. And in some cases, if you can get a 10% or 50%, or in some cases you can get a fairly good 50% improvement, that means not only that you can lower your running cost on Lambda. If you have bare metal machines, it means that you can do more with the same hardware that you have. And that translates consequently to not only lower costs, but much lower energy consumption. Am I missing something?
I think the summary slide.
Yeah.
Mm-hmm. Yeah, so in summary, again, today on this particular application, our findings show, that Rust is faster than Java. There's a number of reasons for that. I think Esteban pointed out using Growl to get ahead of time compilation is, brings us brings Java a lot closer. And we do see that the JIT kicks in, and a really good optimized just-in-time compilation with all the knowledge of the current system it's running on can potentially optimize, close to Rust or even the same as Rust in certain circumstances. But things change all the time. And we can see that Rust is more economical than Java. While Java can hit the performance of Rust, it can't do so within the same memory constraints. So a second major finding, Lambda on Graviton today on this application has similar performance to x86, sometimes a little worse, sometimes a little bit better, but universally more energy efficient than x86 and is cheaper than x86. So
we do need to highlight this was on Graviton 2, which is, there are major improvements in Graviton 3.
Yeah, Lambda today is based on Graviton 2. And as I mentioned earlier in this presentation, Graviton 3 is a pretty substantial leap. So as Lambda starts migrating to, or Graviton 3 offers that option, there's going to be even more benefits there. So your applications may vary. One thing to take away is that in the first example that Esteban was going through, they wrote 4 versions of Java to get that optimized. Is it really worth rewriting in Rust and doing another 3 iterations on Rust to get a truly optimized application for the workload? Maybe. It depends on your application, and sometimes that level of optimization and rewriting is worth it. Oftentimes, it's not broken, you don't want to fix it. And so if the performance is good enough and the cost and energy usage is good enough, then it might be better to leave the application in place rather than creating something new with all the maintenance and support that requires. So it's a judgment call there. And then in another, this is what happens today and things evolve. Another moving piece here is the Lambda ecosystem. I already mentioned Snap Start being released. They are constantly doing optimizations on Lambda to improve cold starts, improve warm runs as well, and so that service is going to continue to evolve and get better over time, and that will change some of the numbers that you see.
And as you said, in the case of SnapStart, that brought down the cold start latency for a sample application written in Java down from 6 seconds down to 200 milliseconds. The Rust version without SnapStart, of course, was around 100 milliseconds for the cold starts. So there is still some winnings there, but as the platform evolves, you get the benefits of that evolution.
Yeah, this is such a new feature. I should also add that SnapStart is a feature that you need to opt into in Lambda. So it doesn't just kick in for anybody that's already using Java Corretto 11. It's something that you need to deploy your Lambda function and specify specifically, I want SnapStart.